Hello and welcome to another math video. Today we are walking through this mathematical proof by induction problem where we are proving that the sum of cubes is equivalent to taking the sum 1 to n and squaring it. So we can begin this problem by starting with our base case where we are going to prove that for n equals 1, p of 1, this statement holds. So let's put 1 in for n. So that would be 1 cubed is equivalent to 1 squared. And we know that's true because 1 cubed is 1 and 1 squared is 1. So that is a true statement. Our next step is to do our inductive hypothesis, where we are going to assume that p of k is true. So all we're going to do here is rewrite the claim we were given above, and instead of n, we'll go all the way to some value k. So 1 plus 2 plus 3 plus all the way to k, that whole value squared. Assume that's true. And then our third step is the inductive step, where we are going to show that p of k plus 1 is true. And let's send that board up for that. Just that, and pull this other board down. So the way we're going to do that is by plugging in k plus 1 into both sides of our statement. So 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed plus k plus 1 cubed. And then we're saying it's equivalent to 1 plus 2 plus 3 plus all the way to k plus 1, that whole thing squared. And I think the side that I want to work on manipulating is the right-hand side. It doesn't really matter which side you want to use, both sides, as long as you're performing valid mathematical operations, both sides work. There is sometimes a side that's going to be easier than the other. But looking at this equation, what I'm seeing is that on the right-hand side, I'm getting something pretty similar to the structure of a binomial. So something like a plus b squared. It's kind of what I'm seeing here, where if we pretend that this whole side is a and our k plus 1 term is b, we have sort of an a plus b squared situation. And hopefully you remember that a plus b squared is equivalent to a squared plus 2ab plus b squared. So if we follow that formula, that kind of simplified version of what we have here with a lot less terms, we can rewrite what we have on the right-hand side to be 1 plus 2 plus 3 plus all the way to k squared plus, kind of running out of space here, but that ab term, so the sum all the way to k, and I'm going to rewrite that for the sake of space. We're going to say from n equals 1 to k of, call it x, times our b term, k plus 1, and then adding that b squared, where our b is the k plus 1. So we're going to say k plus 1 squared. So those are all equivalent statements. And what I think I want to do next is think of the other way we can represent the summation of all numbers 1 to k. And hopefully you remember that sum of all those numbers from n equals 1 to n is equivalent to n times n plus 1 all over 2. So we can pull this formula down here, where we're going from 1 to k instead of 1 to n, and we'll get k times k plus 1 over 2. That whole thing squared, remember, because we're squaring this, but the formula we have here is not squared. And then we can add 2 times, and then remember that a term is the same thing we have here. So let's pull this formula down again. So k times k plus 1 all over 2. And then times k plus 1, which just came from up here, plus that k plus 1 squared. So what I want to do next is see if there are any things that I can cancel or any fractions that I can simplify. And I actually am seeing one where we can cancel out this 2 in the numerator and this 2 in the denominator. So we get rid of that, and we no longer have a fraction right there. And then I am also seeing that we have this k plus 1 multiplied by this other k plus 1, which will get us a k plus 1 squared, which we actually already have over here. So I'm wondering if we can factor that out. But we will save that for our next step. So let's rewrite what we have, but without that fraction in our second term. So k times, I'm just going to skip to k plus 1 squared, right, because we already see these terms here, which would get squared. And then k plus 1 squared, which again just comes from that last term. And then I'm seeing that these two terms have a factor in common. So what can we do there? We can pretty simply factor that out. And then again, pulling this first term, I haven't touched it at all. I haven't done anything to it. And then we're going to factor this out, right? Because we're going to get k plus 1 as our first term times k plus 1 squared, right? Because we're factoring out that k plus 1 squared, and we have a k times k plus 1 squared here, and then that imaginary 1 that's right there. So we have k plus 1 times k plus 1 squared, or just more simply, k plus 1 cubed, and we can keep going. K times k plus 1 all over 2. Again, that hasn't changed at all. Plus k plus 1 cubed. And now I am looking at what we have, and I am thinking that this term, we kind of can't really do anything with it. And I'm wondering if we should just change that back into a different form out of that formula we borrowed above, where we said the summation of all terms from 1 to k is k times k plus 1 over 2. What else I'm noticing is that this term actually looks pretty familiar from something we did above, where we said the summation of all terms is equivalent to something else here from our inductive hypothesis. So let's do this actually one step at a time, where we'll say this is equivalent. We'll just put it back into this listed notation, 1 plus 2 plus 3 plus all the way to k squared plus k plus 1 cubed. And now this probably looks a little more similar. It's maybe easier for you to imagine how this can become what we used in our inductive hypothesis, where the square of the sum terms 1 to k is equivalent to the sum of cubes. So let's transform that by the inductive hypothesis. And we'll say 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed plus k plus 1 cubed. And that is exactly what we were going for from the beginning. So the way I knew not to touch this last term, which I think is one of the harder parts of this proof, to know to not multiply this whole thing out and get some kind of like k cubed situation going on is because I'm looking at this k plus 1 cubed, and I'm noticing that comparing back to what we were doing at the beginning of this proof, where we wanted to get both sides to be equivalent, I already saw that we had this k plus 1 cubed here, and I wanted to keep it. So anything I see that looks like something I want to keep or something that already exists on the side I'm trying to get equal, then I kind of want to leave it alone and see if I can do anything with everything else. Because I knew I already had this k plus 1 cubed term. I knew I wanted to keep it, and everything else is probably correct. I just need to somehow get the rest of what I had here in my first term to look like everything before the k plus 1 cubed. So at the end, I am just going to say the left-hand side LHS is equivalent to 1 cubed plus 2 cubed. I'm just rewriting what we got, plus all the way to k cubed plus k plus 1 cubed, saying that's equal, and that is the end of our proof. Thanks so much for watching. I hope you learned something from this video, and remember to keep on trucking.